as we continue our discussion on linear independence, I'll start with this little question. Now that we've got our hands around what linear independence hopefully is and how to determine it, is the set of vectors here linearly independent or linearly dependent? And if you'll notice, there are different vectors, and then notice I've added another vector in the set, a zero vector. Okay, is this set linearly independent or not? We won't look ahead. Let's take a look and see how we can answer this question and understand what's going on here. So again, what have we done to determine linear independence so far? I take a linear combinations of the vectors in the set. So I'm going to do that this way, all the way to KR, VR, and then I need to add some scalar multiple of the zero vector, and I've got K1 for V1, K2 for V2, KR for VR. I'll just call this K. I mean, just K times 0, right? Equal to zero vector. Now, so here I have, so what do we take to determine linear independence? Remember, if the K1 through KR and the K are all 0, we have a solution, right? Because again, that's the trivial solution that always exists. The question is that the only solution, right? If that's the only solution, then they're linearly independent. But if there's a non-trivial solution, right, one in which at least one of these coefficients is not 0, then the vectors are going to be linearly dependent. Okay? Well, can you think of specific values, perhaps, for all these coefficients, K1 through KR and K, that will satisfy this equation, that will make the result 0, but where not all of the coefficients are equal to 0? So again, it certainly works with K1, K2, KR, and K are all 0. This is true. But can you find a solution, values of K1 through KR and K, where they are not all equal to 0, but still satisfy this equation? All right. Did you come up with it? Well, how about this? I'm going to let K1 be the same as K2, be the same as K3, be the same as K4, be the same as all the way up to KR. I'm going to let all those be 0. So wait a minute. Let them all be 0. Well, don't forget we've got K. So I'm going to let all those be 0, and I'm going to let K simply be not 0, like 2 or 10 or negative 11. It doesn't really matter, because what am I multiplying K by? The 0 vector. Anything times the 0 vector is what? The 0 vector. Right? So it doesn't matter what K is, this will always be 0. So technically I can choose K to be something that's not 0. But the minute I do, right, the minute I have something that's not 0 as one of my coefficients at least, that makes these vectors linearly dependent. So what does this mean? This means that a set of vectors that includes the 0 vector is always linearly dependent. So if you have the 0 vector in the set, then the set is linearly independent. It doesn't mean every linearly dependent set has the 0 vector in it. We've already seen a case in the last video where that was the case. But if you do have the 0 vector in it, it's automatically linearly dependent. Okay? Now, this also gives me, finally, we can go to a set of one vector. When is a set of one vector? If there's just one vector in there, how do we know if it's linearly independent or not? Well, it's linearly independent if and only if it's not the 0 vector. So if there's just one vector in the set, if it's non-zero vector, the linearly independent. If it's the 0 vector, it's linearly dependent. Okay. So some facts that you'll need to remember. Good true-false questions, so make sure you review those in the textbook and think about these ideas. Now, nice little theorem here that we'll enhance upon later. But we have here a set of vectors. Right, there's R vectors, and they are in n space. Okay. Now, if R is greater than n, then this set S is linearly dependent. All right. Let's see how we can prove this. So what are the values of R and N? What significance do they have? Well, I mean, if I'm going to, again, set this up to determine linear independence, I take a linear combination of these vectors. I've done this umpteen times now. And I set it equal to the 0 vector. And this is going to give me a system of linear equations, right? System of linear equations. How many unknowns am I going to have in that system? How many unknowns am I going to have? Well, the unknowns are these coefficients, k1, k2 to kr. There's r unknowns. And how many equations are we going to have? Do you remember from the last video how we determine the number of equations? Depends on what space our vectors are in. What space are they in? N space. These are n tuples. Each one of these vectors is n tuples. And we get an equation for each component, right? And if there's n components, these are n tuples, then there's n equations. Okay. So when I look at this solving for k1 through kr, I'm going to get a system of equations, ax equals 0, right? Where I have r unknowns and n equations. Right? R unknowns and n equations. Notice r then is the number of what? Columns or rows of A. The number of unknowns is what? The number of columns, right? So r equals the number of columns of A. And n is equal to what? Each equation gives us a row, right, for the matrix, coefficient matrix A. Number of rows of A. Okay. Now, what do? We solve this system, and we're looking to see are there non-trivial solutions, right? Are there non-trivial solutions? Well, to determine whether there's non-trivial solutions, what are we going to look for? We need to see, is there a column, when we take the matrix A and put it in reduced echelon form, is there a column that does not have a leading 1 in it, a column corresponding to one of our unknowns? If it does not have a leading 1 in it, then that's a free variable. We have a parameter, we have an infinite number of solutions, and therefore they're going to be linearly dependent. All right, so that's the case if they're linearly dependent. Well, let's think about that. What is when I put A in reduced echelon form? What's the most number of leading ones in the reduced row echelon form of A? What is the most number of leading ones I can have? Well, we know that there are n equations, right? N equations. And so the most I can have is 1 for each equation. 1 for each equation. Right? But since r is what? In this case, here's the kicker. R is greater than n. Right? The most number of leading ones I can have is n. I can't have more, right? Because why? I can't have more than one leading one per row. Each row has what? One leading one. So if every row has a leading 1 in it, I'll have n. I can't have more. But r is greater than n. What is r? The number of columns. Each column of A corresponds to one of our unknowns. If r is greater than n, that means what? There's at least one column without a leading 1. Other than, of course, the last column, which has all the zeros, right? There's at least one column corresponding to a coefficient, to an unknown, without a leading 1. And therefore what? There's at least one free variable. Or parameter, right? And therefore infinitely many solutions. And therefore linear dependence. Okay. This is not a very well written proof, just kind of talked you through the idea of the proof, but that's the nuts and bolts of it. Okay, so in the case where I have what? R equations, sorry, R vectors in a set that reside in n space, right? If I have R n tuples, if R is greater than n, then the set is linearly dependent. So let's look at a specific example. If I have 4 vectors in 3 space, I have 4 ordered triples, right? 4 would be the value for R, right? 4 vectors here, and they'd be in 3 space, so n would be 3, right? Well, in that case, R is 4, n is 3. That means the set is linearly dependent. So if you have 4 vectors in 3 space, 4 or more vectors in 3 space, they're linearly dependent. You don't have to check anything. If I have 5 vectors in 4 space, linearly dependent. If I have 6 or more vectors in 5 space, linearly dependent. Don't have to check anything. Okay, so now if I have 3 vectors in 3 space, well, I'm going to have to check right now. If I have 3 or fewer, I'm going to have to check, see if they're linearly independent. But if I have more vectors than the dimension, well, so I use the word dimension, we'll prove that a little bit later, but you know, in n space, I have more than n vectors in the set, then they are linearly dependent. Okay. We'll close with an example of determining linear independence for a set of vectors in a different sort of vector space. So remember we've talked about, oops, let me focus in on that a little better. So P sub 2 is what? The set of all polynomials of degree 2 or less. That forms a vector space. And so I'm going to take a look at this. Are the polynomials in P sub 2, and here are my 3 polynomials. Are they linearly independent or linearly dependent? Okay. Well, we're going to do the same thing. I'm going to take a linear combination of these vectors, and they would be boldface again in the book. I put arrows over them. But these vectors, notice, are not ordered triples or ordered pairs or whatever, ordered n tuples. They're polynomials. They're polynomials, right? And therefore the 0 vector is a polynomial. What's the 0 vector in this polynomial space? Well, it is 0 plus 0x plus 0x squared, or just 0. Right? That's the 0 polynomial, where all the coefficients are 0. Okay? So how do I solve? So what I'm looking for, is there values of k1, k2, and k3 not all 0, such that this equation is satisfied? If that's the case, they're linearly dependent. If it's the only solution, then they're linearly independent. Okay? So what do? K1 times P1, what's that? Just multiply, distribute, right? K1 plus K1x plus K1x squared. Right? There's K1 times P1. K2 times P2. 3K2 minus K2x minus 5K2x squared. And then plus K3 times P3 plus 4K3 plus 2K3x squared. And that equals, again, I'll just write 0 plus 0x plus 0x squared. Okay. And now, you know, again, how do you add polynomials together? Well, we combine like terms. The constant terms are what? K1 plus 3K2 plus 4K3. Right, so I'm just combining like terms here. And what do we know about these constant terms? What do they have to equal? Well, in this equation, they all have to equal what? What's the constant term over here? It has to equal the constant term over here. Just 0. Right? They're all equal to 0. What about the x terms? Well, what are the coefficients? I add the coefficients together, right? So the coefficients of the x terms are going to give me K1 plus a negative K2 or minus K2 plus 0. There's no x term here. And what do the coefficients of the x term have to add to? 0. And then what's the coefficient of x squared terms? k1 x squared minus 5k2 x squared plus 2k3. And what do these coefficients have to add up to? What's the coefficient of x squared over here? 0. Okay. Notice there's no x's in here, right? These are the constant terms, the x terms, the x squared term coefficients, right? The coefficients. And so that's what these are. These are the constant terms, the x coefficients, and the x squared coefficients. Right. So how do we determine linear independence? You can solve the system, or just note again that this system is ax equal 0 with a equal to this matrix, the coefficient matrix. In this case it's square, and so I can go ahead and take the determinant of this matrix, and I get negative 24, which is not 0. The determinant of this matrix is negative 24, again, using technology, using a calculator. And that means what? Because a is square, the system ax equals 0, what? What do we know about it? Since the determinant is not 0, that means what? A is invertible, and ax equals 0, what? Has what? Only the trivial solution. And therefore, what do we know about the polynomials? They are linearly independent. Again, you could have solved the system if you wanted to. You can write the augmented matrix, put the zeros on here, solve the system. What are you going to get? We already know the reduced echelon form of A must be what? The identity matrix. And so we get only the trivial solution. And again, we'll reach the same conclusion. Okay. So we can do linear independence of polynomials. We can do linear independence of matrices in much the same way. So if you look at the homework set and in the textbook, you'll see some examples like this, and so you'll get some practice doing some of those types of examples. Okay, so next thing we're going to look at then is the idea of dimension. We are about ready to take a look at dimension and then what we call basis.